Alright, ladies and gentlemen, so welcome to video installment number 2, where we're going to talk about the absolute age of rocks. I hope everybody's staying home, being safe, and everybody at home is healthy. So when we talk about absolute age of rocks, what we're talking about is putting a number. The age of the rock in years. It's called its absolute age. In the instance of rocks, we're going to use millions of years. And the way that's done is by actually taking a radioactive element and measuring the amount of it in a certain rock compared to what it would have broken down into. So for the instance of rocks, we're going to use an isotope called uranium-238. Uranium-238 breaks down into lead, and those are found in the mineral zircon. And what we can do is use zircon crystals, and actually zircon replaces lead with uranium-238 readily, so we can actually find that element in those minerals, and it actually will decay at a known rate or break down at a known rate. So what happens is we use an isotope. An isotope forms from the same element, but what happens is it has the same number of protons but a different number of neutrons in the nuclei. Can you guys think of an element that you used in biology to talk about this, about dating more recent organic remains? This element is only used in recent organic remains. That would be carbon-14. But that has a different atomic mass, all right? But it still reacts the same. It has the same chemical properties. So if we take a look at how radioactive decay works, we take a radioactive atom, and that atom is unstable. That atom wants to break down. It's not going to stay in that form. It's not going to stay in the isotope form forever. Some last longer than others. In the instance of carbon-14, carbon-14's half-life is very short, and the telephone's ringing just like it does it. Okay, this time the phone call was guidance calling my mother-in-law down, see if she could get extended time to watch her soap operas. So we were talking about carbon-14, and carbon-14, it breaks down into nitrogen-14, and it releases a radiation. So radioactive decay is the process by which the unstable atomic nucleus loses energy by emitting radiation in the form of a particle, such as an alpha or beta particle. We don't really need to memorize which particles, but we do need to understand that it breaks down from one isotope to a daughter product. And what happens with that, we'll use carbon-14 again, since you guys already learned about that. Carbon-14 will break down into nitrogen-14. Now notice the atomic number of carbon, the atomic mass of carbon is actually 12, and the atomic mass of nitrogen is 14. So when carbon-14, which means it's a heavier element than its regular stable product, it will break down into nitrogen-14. And when that happens, it actually releases a beta particle. So what you have is a beta decay, and you take the parent isotope, and that will break down into the daughter product. Now, if we look at our Earth Science reference tables on the front cover, what you'll see is a radioactive decay chart. And these are all the different elements that we're going to use. If we look at carbon-14 here, we'll see it's carbon-14 breaks down into nitrogen-14, and we're going to use scientific notation. So remember, this is going to add 3 places after the decimal point, so that's 5,700 years. So it's going to add 2 zeros, 5,700 years. If we look at potassium-40 will break down into argon-40 and calcium-40. We don't know which, and we don't know if it'll vary, but those are the 2 elements that you would measure when using potassium. If you look over here, its half-life is 1.3 billion years. So that has quite a long half-life, more used for rocks than it is for recent organic remains. Now, the most common one used for rocks is going to be uranium-238, the one I talked about earlier. That's going to break down into lead-206. Now, those numbers don't match because there's a lot of things that goes on in between uranium-238 and lead-206. You're going to learn more about that when you get to chemistry, but we're really not going to have to worry about that here. So for our purposes, just remember that it breaks down from uranium-238 to lead-206, and you don't need to memorize it because it's right here on the Earth Science Reference Table. That takes 4.5 billion years for that to break down. And rubidium-87, if we look at that, that one breaks down into strontium-87, and that takes 49 billion years because that's a 10 to the 10 power. So that's going to be 49 billion years. Now, if we take a look at what a half-life is, a half-life is the amount of time required for the quantity to reduce half its remaining mass. So therefore, if we start with a hole, after one half-life, we are going to have 50% carbon-14 and 50% nitrogen-14. Or if it's uranium, we're going to have 50% uranium-238 and 50% lead-206. That amount of time that it takes to break down is going to be its half-life. We don't know which atoms are going to break down. We just know that that amount is going to break down in that amount of time. So what you have is the next half-life, you're going to take the remaining mass of carbon-14, and that would break down by half. So after another 5,700 years for carbon-14, what you'll end up having is 25% of carbon-14 and 75% of it will be nitrogen-14. Now, if we take a look at an example of a Regents question, how they ask you this, what you have here is a generic decayed atoms versus undecayed atoms. So if you count up the total number of boxes, you have 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6, 7, 8. So 4 times 8 is 32. So if you have 32 total boxes and you have 1, 2, 3, 4, 5, 6, 7, 8 boxes left that are undecayed atoms, how many half-lives has this radioactive element undergone? So after one half-life, what you have is you take the total number, you divide that by 2, and it'll leave you with 16 atoms. Now, after another half-life, you're going to take that 16 and you're going to divide that by 2. And what does that equal? That equals 8. How many undecayed atoms did we have? We had 8. So how many half-lives did it undergo? 1, 2 half-lives. Now, if we take a look at this on a graph, what we see is the dark line is going to be the radioactive isotope, and the dashed line is going to be the daughter product. So if you look, you have your typical U-shaped graph. You have proportion of parent isotope and proportion of daughter product. So what you have is you start out with 100%. After one half-life, you have 50% of the radioactive isotope. After 2 half-lives, you have 25%. After 3 half-lives, you have 25 divided by 2, 12.5%, and so on. Now, as the decay happens, you start out with 0 for the daughter product, and what happens is then that goes to 50%. In this instance, it could be carbon-14, and then 75%, and so on. So if we look at the mass of the original isotope and the mass of the daughter product, it's not daughter isotope, you're going to see this type of graph. So half-life is not altered by the environmental factors. The half-life of a substance does not change. So that means if you increase the pressure, half-life doesn't change. You increase the temperature, half-life doesn't change. You set it out in the rain, half-life doesn't change. No matter what you do to the element, the half-life does not change. It's going to break down in that amount of time. So if we look at a chart of this, and we take and we put carbon-14 in blue and nitrogen-14 in red, and this is the original isotope when it starts. So it hasn't gone on any change, so there's 0 half-life. We have 100% carbon-14, and we have 0% nitrogen-14. Now let's make up a number, and we're going to say 100 grams of carbon-14. So if we undergo change here, all right, what's going to happen? If we undergo change, we see that 50% of the carbon-14 has changed into nitrogen-14. So we've undergone 1 half-life. Now we have 50% carbon-14, 50% nitrogen-14. We have 50 grams of carbon-14 and 50 grams of nitrogen-14. Undergo another half-life, the remaining mass changes by 50%. Now notice that. The remaining mass over here of the carbon-14 is what's affected. That changes and reduces by half. So now you end up with 25% of carbon-14, 75% nitrogen-14. It has undergone 2 half-lives. Therefore, you have 2.5 grams of carbon-14 left and 7.5 grams of nitrogen-14. Now let's undergo one more half-life, and what you end up with is 12.5% of the carbon-14, and you end up with 87.5% of the nitrogen-14. And that undergoes 3 half-lives. How many years old is this substance? So if we take a look at this, we have 3 times 5,700. So therefore, this substance is 17,100 years old. Okay, so our important isotopes, uranium-238, this is important because it gives us the half-life of a very old element, so therefore we can use it for the age of the Earth. So now, if you look at your reference tables and look up the half-life of uranium-238, and then look up the age of the Earth, how much uranium-238 is left on Earth from the original formation of the Earth? Half. Because if we look at it, we see that the Earth is 4.6 billion years old. The half-life of uranium is 4.5 billion years old. So therefore, we have about 50% remaining. Now, if we look at carbon-14, carbon-14 has a relatively short half-life. It's only 5,700 years. So therefore, it's only going to be good for recent organic remains. And that means less than about 75,000 years. Why? Because it's all going to be used up by the time you get to 1 million years. And if we look at, what are we talking about with recent organic remains? We're looking at the remains of the Iceman that was found in a glacier, and then they can date how old this guy was based on the amount of carbon-14. Now, what we're going to do is we're going to do a decay penny lab. And you can watch this video that's linked in the PowerPoint. And with this video, you actually are also going to get a lab sheet that's posted in Google Classroom. You're going to need about 100 pennies. You can also do this with M&Ms. And what you do is you put them in a cup, you shake up the cup, and then you're going to drop those onto a table. And what you're going to do is you're going to take away every one of the pennies that is on heads. And you're going to then put the rest of the pennies that remain in a cup, and then you're going to shake that up and you're going to spill it again, recording your numbers every time you do this. So if you watch in the video, you're going to see that the girl that does the activity, the first time she dumps the pennies, she ends up with 58 pennies, all right, decayed. So therefore, she marks 58 on her graph. All right, and you guys are going to make a graph very similar to what's in the video. So what you can do is you can then take a picture of your lab and take a picture of your answers and submit it to Google Classroom. And if you have any problems with this, please contact me, and I'll make arrangements with you on how to handle it. Again, everybody stay happy, healthy, and If you have any problems, please feel free to email me and contact me. Somebody did